My project, along with Gabe, who's not here, is designing a low-cost, upper high frequency radio frequency identification transceiver. So throughout this presentation, I'll go through the project goals, design parameters and specifications, the basics of RFID, how the tags work, the interfaces, the possibilities that we had to choose from, and how we made a decision on the interfaces between the boards, the overall design of the hardware and the software, the results that we currently have, and a brief summary. So the main goal of this project was to create a system that identifies objects using radio frequency identification, or RFID. Like Dr. Katz said earlier, this could be used for like theft protection in stores. So this is a combination of hardware, which I mainly worked on, and software, which Gabe mainly worked on. So the hardware includes the receiver and the transmitter and the connections between them, and the software is a computer program that basically controls all the communication between the components. So the design parameters include an operating frequency of 915 megahertz. This is in like the global band of frequencies, which means that we chose this so we didn't have to get like a license for our project. The supply voltage of 3 to 3.6. I think the port we chose was 3.3. So how we got power was from the computer, so through USB. So the computer provided 5 volts, and each board has its own voltage regulator, which regulates the voltage down to the 3.3 volts that is needed for the board to operate. And the tag size will be roughly 5.3, but yeah, 3.3 centimeters of paper tag on the environment from -40 to like 85 degrees Celsius, and an operating distance of up to 3 meters. So the basics of RFID communication include well, the computer basically controls all the communication. So the computer sends sends the signal. There's like a microcontroller. This could be like the main microcontroller could be like a separate thing, or in the case of this project, we have a microcontroller on each board, one board for the transmitter and one for the receiver. So the signal gets sent to the transmitter, which then gets sent to the tag ultimately. And then the tag creates like its own signal and sends it back to the receiver, which ends up sending it back to the computer. So how the tags work, there's a difference between passive tags and active tags. So the passive tags do not have their own power supply, which ultimately creates like a smaller operating distance for them. And the active tags have their own power supply, which could be used for a larger operating distance, but they're also usually more expensive. So both of them contain a circuit to take in, like an antenna to take in the signals, process them, and then transmit their own signal back to the receiver. So for this project, we went with the passive tags because of the lower cost, and the operating distance was within what we needed. So the possible interfaces that we thought of for the interactions between the two boards include SPI, or serial peripheral interface, or the I2C interface. So the SPI includes 3 communication wires. One is MOSI, or master output slave input, and the other one is MISO, master input slave output, and then there's a clock. The clock is one directional from the master to the slave board, and both the wires, the MOSI and the MISO, are also one directional from whereas the I2C communication has one wire for transmitting data and the other wires for the clock. So we thought it was easier to program for SPI because of the 2 separate wires, and also both boards would be able to send data simultaneously because of the 2 wires instead of just 1 wire. So the components, there was a lot of process between trying to choose, I guess, the best components. So based on availability and simplicity, we ended up choosing 2 of the EFR32XG Pro kits, which comes with the radio board, the antenna, has pins for the SPI connections and the UART and all that. We also need the computer, obviously, for the software program. Needed a multi-port USB cable because each board, so 2 of the 2 for powering each board, and then the 3rd is for the UART connections to transmit the data to the board. So this is the overall pin diagram of how it's set up. We have a computer, like I said. The 2, here and here, I think you can see the cursor, are for the powering the boards. And then this is the UART USB for transmitting the data to the master board. Okay. Everything goes through the master board. So how the UART connections work is that the transmit pin goes to the receive pin, well, it just says P11, but that's the receive pin on the master board, and vice versa for the receive. So the receive will go to the transmit, and then, sorry, kind of look old. These 3, the pin 1, 3, and 5 are for the SPI connections, which these are directly connected, unlike the UART, which is inversely connected, I guess. And then each board has the radio board, which I didn't put it on here, but each radio board would have the antenna that sticks up for the transmission with the text. Okay. Basics of the software configuration. So there's 2 programs, one for the master board and one for the slave board. We're a little behind, so what we're currently able to implement is the 3 cases for the SPI communication between the boards, which includes a command from the terminal to blink an LED on the master board, for one, to start with. And then when a button is pressed on the master board, when it's released, it would blink the LED on the slave board. And the receipt is sent to the terminal. I'll show that a little later. Along with when a button is pressed on the slave board, when it's released, the LED on the master board would light up and the receipt sent to the terminal. Like I said a little bit previously, the master, everything goes through the master board. So the master board controls everything, and all of communication, like the button push and everything is based on it is interrupt based. Okay. So to preface this, this is just a video of like how communication works. Like when I push, well, a button on one board, the LED on the other board lights up. Okay. So I press a button on the master board, then the LED on the slave board lit up. Then vice versa. Pressing the button on the slave board lit up the button on the master board. And these are the results from the terminals when I was doing that. So first I just typed blink in the terminal to blink, that wasn't shown in the video, but to blink the LED on the master board. And then when I push the button on the master board, it prints sending ping to slave. And then when that's received, it prints received ping from master. Okay. Then vice versa, when I press that button on the slave board, it prints on the slave console, sending home to the master. And then when it's received by the master, it prints received home from slave. Then it would light up the LED on the master board. Then just a brief summary. The overall goal was to create an RFID system that could be used to identify objects. While this hasn't happened yet, because this will continue onto next semester. So currently we just have the SPI communication complete, and next semester Gabe will be continuing this project with programming the system to interact with the tags.
Are there questions? Looks like a very interesting project in a lot of ways you can go, Kathy. Have you thought about different types of tags or anything as an extension on this?
I still have some options for like what tags we're specifically using, but we do know that it's the passive tags, paper tags, and within like the upper high frequency range. So they'll be able to, sorry. But within the 3 meter distance